In the avian world, size and weight are critical factors that determine whether a bird can take to the skies. Among modern birds, the two biggest and heaviest are the Andean condor and the wandering albatross. The Andean condor, with a wingspan of up to 3.3 meters and a weight of about 15 kilograms, and the wandering albatross with a wingspan reaching up to 3.5 meters and a weight of around 12 kilograms, are remarkable flyers despite their size. However, there is a limit to how large a bird can be before it becomes too heavy to fly. This limitation is well understood by ornithologists and is rooted in the principles of physics and biology. Now, imagine a creature far larger and heavier than these modern giants, a creature named Quetzalcoatlus. This prehistoric flying reptile dwarfed even the largest birds of today, boasting a wingspan of up to 12 meters and a weight of around 250 kilograms. Quetzalcoatlus lived during the Late Cretaceous period, soaring above the dinosaurs. Its size and weight make it a fascinating subject of study, particularly in light of the fact that modern birds of comparable size cannot achieve flight. This raises an intriguing question. Why can't large birds fly today? And what has changed since the time of Quetzalcoatlus? To answer this, we must delve into the evolutionary and ecological changes that have occurred over millions of years and examine the unique adaptations that enabled Quetzalcoatlus to dominate the skies. Body. Among contemporary birds, the largest species that cannot fly include the ostrich and the emu. The ostrich, native to Africa, is the world's largest bird, standing up to 2.7 meters tall and weighing as much as 145 kilograms. The emu, native to Australia, stands about 1.9 meters tall and weighs up to 60 kilograms. These birds have evolved to be powerful runners rather than flyers, with strong legs adapted for speed and endurance on the ground. The scientific consensus on the limitations of flight for large birds centers on the relationship between body weight and wing loading, the amount of weight each unit area of the wing must support. As birds increase in size, their weight increases cubically, while their wing area increases only quadratically. This disparity means that, beyond a certain size, birds would require disproportionately large wings to generate enough lift for flight, making flight energetically inefficient and impractical. Hence, large birds have adapted to life on the ground, where their size offers advantages in terms of survival and reproduction. Quetzalcoatlus, named after the Aztec feathered serpent god Quetzalcoatl, was an astonishingly large pterosaur that lived around 70 million years ago. With an estimated wingspan of up to 12 meters and a body weight of about 250 kilograms, Quetzalcoatlus was one of the largest, if not the largest, flying creatures to have ever existed. In comparison, the Andean condor and the wandering albatross seem diminutive, highlighting the extraordinary size of this prehistoric flyer. Quetzalcoatlus thrived during the Late Cretaceous period, a time when dinosaurs roamed the earth. It was a time of diverse and abundant life, with complex ecosystems that supported a variety of large and small species. Quetzalcoatlus, with its impressive wingspan and lightweight yet strong skeletal structure, was well adapted to dominate the skies. However, it met its end around 66 million years ago during the mass extinction event that wiped out the dinosaurs. The story of Quetzalcoatlus's discovery began in 1971 when a team of geologists from the University of Texas was exploring the fossil-rich grounds of Big Bend National Park. Amid their search for dinosaur fossils, a young geology student named Douglas Lawson stumbled upon an unusual bone, a wrist bone as large as a frisbee. Intrigued by this find, Lawson and his team began excavating the area, uncovering more bones that would later be identified as parts of a massive flying reptile. Upon returning to the university, the team meticulously pieced together the bones and reconstructed the creature. They were astonished to realize that they had discovered the largest flying animal ever known, which they named Quetzalcoatlus northropi. The sheer size of the wings and the estimated weight of the creature posed a significant puzzle to scientists. How could something so large achieve flight? This discovery not only challenged the existing understanding of flight mechanics, but also opened new avenues for research into the capabilities and limitations of prehistoric creatures. The idea of a creature as large as Quetzalcoatlus taking to the skies seems almost fantastical. When scientists first contemplated how such a heavy creature could fly, there was widespread skepticism. The physics of flight imposes stringent limits on size and weight, and many doubted whether Quetzalcoatlus could have been airborne. The primary challenge lay in understanding how an animal weighing up to 250 kilograms, 550 pounds, could generate enough lift and thrust to sustain flight. Enter Paul McCready, an aviation engineer who took on the challenge of solving this mystery. In the early 1980s, Macready built a series of remote-controlled models of Quetzalcoatlus to test its flight capabilities. His models were carefully constructed to replicate the physical characteristics of the pterosaur, scaled down to a manageable size. One of the significant findings from these experiments was the role of head movement in maintaining stability during flight. Unlike modern birds, which use their tails for stabilization, Quetzalcoatlus appeared to use its long, flexible neck to balance and steer itself in the air. Despite the insights gained from Macready's models, not all scientists were convinced. Paleontologist Kevin Padian raised critical points regarding the flight model. Padian argued that Macready's reliance on a wheeled launch system did not accurately represent how Quetzalcoatlus would have taken off in the wild. He also questioned the direct scaling up of a small model to predict the flight capabilities of a much larger animal, noting that biomechanics do not always scale linearly. Further studies focused on the biomechanics of Quetzalcoatlus's takeoff. Researchers discovered that this pterosaur likely employed a unique launch method involving a powerful leap assisted by its strong, muscular legs and wings. This quadrupedal launch technique would have allowed Quetzalcoatlus to gain enough initial lift to start flying, despite its considerable size and weight. These findings underscored the complexity and specialization of Quetzalcoatlus's flight adaptations, highlighting an evolutionary path distinct from that of modern birds. The evolutionary journey of Quetzalcoatlus is a fascinating tale of adaptation and survival. This pterosaur is believed to have evolved from small, ground-dwelling reptiles that lived approximately 240 million years ago. Over millions of years, some of these reptiles developed membrane-like structures between their limbs, enabling them to glide from tree to tree in pursuit of insects and to escape predators. This gliding ability provided significant evolutionary advantages, gradually leading to the development of more sophisticated wing structures and the capability for powered flight. As these reptiles adapted to life in the air, they faced fewer predators and could exploit new ecological niches. The evolutionary pressure to optimize flight efficiency drove the development of lighter bones, stronger muscles, and more aerodynamic body shapes. Quetzalcoatlus, with its massive wingspan and relatively lightweight yet strong skeleton, exemplifies the pinnacle of these adaptations. Its ability to fly allowed it to dominate the skies, access a wide range of food sources, and avoid terrestrial predators, securing its place as one of the most successful flying creatures of its time. The story of Quetzalcoatlus and its flight capabilities not only challenges our understanding of biomechanics, but also illustrates the remarkable adaptability and resilience of life on Earth. By studying these ancient giants, scientists gain valuable insights into the evolutionary processes that have shaped the diversity of life we see today. The extinction of Quetzalcoatlus, along with many other species, was precipitated by the cataclysmic impact of the Chicxulub asteroid around 66 million years ago. This event triggered massive environmental changes, including widespread fires, a nuclear winter scenario with drastically reduced sunlight, and significant shifts in climate. These conditions led to the mass extinction of approximately 75% of Earth's species, including all non-avian dinosaurs. Land-dwelling dinosaurs and flying pterosaurs faced different survival challenges during this period. While many large land dinosaurs perished, some smaller species managed to survive. These survivors were likely more adaptable to the harsh conditions post-impact, able to find shelter and sustain themselves on limited resources. In contrast, large flying dinosaurs like Quetzalcoatlus were unable to cope with the rapidly changing environment. Their large size and specialized flight adaptations, which had once been advantageous, now became liabilities. The inability to find adequate food, combined with the difficulty of sustaining flight in a drastically altered atmosphere, led to their extinction. The small land dinosaurs that survived eventually gave rise to modern birds. Their smaller size allowed them to reproduce quickly and adapt more readily to new ecological niches. Over millions of years, these survivors evolved various adaptations that enabled them to thrive, including the development of feathers, which were advantageous for both insulation and flight. The evolutionary paths of modern birds and Quetzalcoatlus highlight different adaptations for flight. Modern birds have evolved several key features that make them highly efficient flyers. These include lightweight, hollow bones, a highly developed respiratory system, and feathers that provide both lift and control. These adaptations allow birds to achieve remarkable maneuverability and endurance in flight, something Quetzalcoatlus, with its enormous size and weight, could not match. In comparison, Quetzalcoatlus' design was akin to that of a large early aircraft. Its massive wingspan and robust skeletal structure were necessary to support its weight, but these features also made it less agile than modern birds. The reliance on head movement for stability and the unique quadrupedal launch technique were specialized adaptations that enabled flight but did not offer the same efficiency and versatility found in modern avian species. Modern birds can be likened to modern fighter jets, sleek, highly maneuverable, and efficient. In contrast, Quetzalcoatlus was more like a heavy bomber, capable of long flights, but lacking the agility and efficiency of its modern counterparts. The evolutionary innovations in modern birds reflect millions of years of refinement, leading to optimized structures and behaviors that support sustained, versatile flight. In summary, the inability of large birds to fly today is rooted in the same physical and ecological constraints that once challenged Quetzalcoatlus. Modern birds have evolved to optimize flight through adaptations that favor lightweight structures and efficient energy use. In contrast, the massive size and weight of Quetzalcoatlus, while impressive, ultimately limited its flight capabilities and contributed to its extinction. The story of Quetzalcoatlus provides a fascinating glimpse into the evolutionary pressures that shape flight capabilities. From the challenges of sustaining flight in a large body to the innovative adaptations seen in modern birds, these insights underscore the dynamic interplay between form, function, and environment in the evolution of flight. For more intriguing insights into evolution and animal adaptations, be sure to check out our related videos. Don't forget to like this video, subscribe to our channel, and leave your thoughts and questions in the comments below. Your engagement helps us bring you more captivating scientific content. See you next time on Get Set Fly Science.